Good morning, students. We are going to discuss today similarity of matrices. Similarity transformation. So we are going to use similarity transformation. It implies that we are going to change from one basis to another basis. So we are going to transform from one matrix to another matrix, from one basis to another basis through similar transformation. We are going to use this formula. When you are going to use this formula, and the P matrix should be invertible, inverse, and we are going to use this formula to obtain another matrix. So this is the old matrix. We are going to use similar transformation, and we will be obtaining another matrix A. B is one basis, and A will be another basis. So we are going to change from one basis to another basis through similar transformation. So we know about a linear transformation, already we discussed. So this is about one basis. When you are going to consider similar transformation, it means that we are going to change from one basis to another basis. So from B matrix to A matrix. So these A and B matrices are called similar matrices. Similar matrices A and B, they will oblige certain properties. They will have the invariant of some properties. For example, when you take A and B, both will have same determinant, same trace, same eigenvalues, and same rank. So those properties will be invariant under similar transformation A and B. So A and B are called similar matrices. So similarity of matrices, it is defined as in linear algebra, two square matrices A and B are considered similar if there exists an invertible matrix B. So there exists an inverse matrix P such that this condition is satisfied. A equals P inverse B P. Or equivalently, we can write on the other way around, B equals P A P inverse. So we can write on the other way around. A square matrix B of order n is said to be similar to a square matrix of A of order n if B equals P A P inverse for some non-singular matrix P. So P must be a non-singular matrix. This transformation of a matrix A by a non-singular matrix P to B is called a similarity transformation. It implies that we are going to change from one basis to another basis. If the matrix B is similar to the matrix A, then B has the same eigenvalues as A. I repeat, so A and B are similar matrices and they will have same eigenvalues, same determinant, same eigenvalues, same rank and all those things. Matrix similarity. Let us start by defining a similar matrices. Definition. Let A and B be n by n matrices if we can find a non-singular n by n matrix P such that A equals P inverse B P. Then we can say that A and B are similar to each other, similar matrices. Now I am going to multiply pre and post multiplying equation 1 by P and P inverse. I am going to multiply on both sides by P and P inverse, pre and post. See, P A P inverse. Similarly here P inverse B P inverse. Now what is P inverse? Identity matrix. P inverse will be identity matrix. So you will have I B I, which is nothing but your B matrix, and here it is nothing but P A P inverse. So you will have B equals P A P inverse. Either way you can write. Either you can write A equals P inverse B P or B equals P A P inverse. Both operations are equivalent. So only then we can have A and B are similar matrices. I is the identity matrix. In other words, in declaring matrix similarity, it does not matter which matrix A and B is on left hand side or which gets multiplied with two other matrices B and P inverse. Similarity transformation and eigenvalues of a matrix are invariant. As I said earlier, certain properties are invariant, certain properties. So when you are going to have similar matrices A and B, certain properties will be invariant, they will not change. They will not change. For example, when you take the trace of a matrix A, the same trace will be for B also. And determinant, eigenvalue, rank, all the properties are invariant under similarity transformation between A and B matrices. So let A and B similar matrices, then they have the same properties. So those properties are invariant. A matrix B is said to be similar to B. B is said to be similar to A if there exists a non-singular matrix A. Of course, matrix should be a non-singular matrix. So let us solve one problem. A matrix B is said to be similar to A if there exists non-singular matrix P. Show that B equals P inverse AP. So we are going to show this one. A is given, P is given. Okay. Our idea is A matrix is given. Our idea is whether we are going to have the same property for B also. So A will have certain properties, correct? Here A will have certain properties. For example, you can take the determinant of A, eigenvalue of A, correct? Rank of the matrix A. Those properties, we are going to have this operation, those properties will be the same for B also. So A and B will have same rank, same determinant, same eigenvalue, correct? Same trace. So those, let us check. So A is given as this, B is given by this matrix P, and P inverse. How to find out P inverse? A 2 by 2 matrix. P. How to find out P inverse? P inverse can be found out just to change the diagonal element first. Okay, first change the diagonal element. So we have changed the diagonal elements. Then change the sign. Very good. See, change the sign for the off diagonal elements. I repeat, change the diagonal elements, then change the sign of the off diagonal elements. See, this is your P inverse. Now, what is given? P inverse AP. So P inverse AP. P inverse is here. Your A is given as this. Your P is here. Okay. So now we will do first. We will go with this one. 2 multiplied by 1 multiplied by 2. This one minus 3 multiplied by 1. So minus 3. So first we will go with these two matrices. So we will have 1 multiplied by 1 and minus 3 multiplied by 2. So that will give you minus 6. Okay. So we have this ultimately after the operation we will have minus 1, minus 5. Stop. So we will have this matrix. When I am going to multiply these two, we will get this matrix. Then after that, this should be multiplied by this matrix, correct? So this should be multiplied by this matrix. So again do the matrix multiplication. Then we have P inverse AP will be minus 1, minus 8, 1, 5, which is nothing but your B matrix. So we have obtained now B matrix. Already we know about A matrix through this operation. This is similar transformation. So similar transformation means changing from one basis to another basis of between two matrices, correct? So we have A matrix, we have obtained B matrix now. And some properties, as I said earlier, they should be invariant. They should not change. They should be invariant under similar transformation. So those properties for A and B will be the same. We will find out. So this is your A matrix. This is your B matrix, correct? So this is your A matrix, and we have obtained B matrix now. What is the eigenvalue of trace of the matrix first? What is the trace of the matrix? 4. What is the trace of the matrix? 4. So one property is equivalent. Second one, suppose we want to find out the determinant. Determinant will be 2 2s are 4, 4 minus 1. So 3. Here determinant is come on. What is the determinant? Minus 1 multiplied by 5. So minus 5. Then next one will be plus 8. 3. Determinant is 3. Here also 3. Correct. 2 2s are 4, 4 minus 1, 3. Here also determinant is 3. Here also determinant is 3. Eigenvalues. they also will be equal. Rank of the matrix. If determinant rank of the matrix is, if determinant is not equal to 0, the rank of the matrix is 2. Here determinant is not equal to 0, so rank of the matrix is 2. Here also determinant is not equal to 0, so rank of the matrix is 2. If determinant is equal to 0, rank of the matrix is 1. For 2 by 2 matrix, you will have to reduce by 1. Is it okay? Rank of the matrix is easy to find out. If the determinant is not equal to 0, the rank of the matrix is 2. Here also rank of the matrix is 2. So now both are equal. So they are similar matrices. A and B are similar matrices. A and B are similar matrices because they have same trace, determinant, eigenvalues and rank. Determinant of matrices A and B are not equal to 0, so the rank of the matrices of A and B are 2. Okay. Now we'll go for some other problem. Show that B equals P inverse AP. So A is given as this, P is given as this, and of course we know that we can also do the same way as we have done earlier. How to find out P inverse? How to find out P inverse? Change the diagonals. Okay, we are going to change the diagonal elements. So we have changed the diagonal elements, correct? And we will have to change the sign. See, we have changed the sign. We will get exactly like this. So we can also do it on the other way around. That is P inverse equal to edge P divided by det P to find out P inverse. So edge P is the cofactor of 1. Okay, cofactor of minus 1. So that will be 1. Cofactor of minus 1 is 1. Okay. Similarly, cofactor of 1 is 1. Cofactor of 1 is minus 1. So we can also do it on the other way around. So first we will find out P determinant. So P determinant will be minus 1, 1, 1. Minus 1 multiply 1 will give you minus 1. Minus 1 which is nothing but minus 2. Edge P. Cofactor transpose, correct? This is what edge P. So we have minus 1, cofactor will be your 1. Okay. What are the cofactor for 1? 1 will be 1. We will have to change the minus sign. So minus. What are the cofactor for this 1? 1. We will have to change the minus 1. What is the cofactor for this 1? It is minus 1. So minus 1. So P inverse will be edge P divided by determinant P. So that will be given as 1 divided by minus 2. Your edge P is this one. So 1 by 2 minus 1, 1, 1. Okay. So B equals P inverse AP. So 1 by 2 P inverse is this one. So 1 by 2 this multiplied by A multiplied by P. So we will have minus 1 multiplied by 3 will be minus 3. 1 multiplied by minus 1 will be minus 1. Minus 1 multiplied by minus 1 will be plus 1. 1 multiplied by 3 will be 3. So similarly, we can have these two matrices 1 by 2 minus 4, solving this minus 4, 4, 2, 2, minus 1, 1, 1. Similarly, you can also multiply these two matrices, you will be getting as 4 plus 4. Minus 4 multiply minus 1 will be plus 4. 4 multiply 1 will be plus 4. So solving this, we will have 1 by 2, 4 plus 4 is nothing but 8. So we have 0, 0, 4. So we have 4, 0, 0, 2. So your B matrix is nothing but 4, 0, 0, 2. What is the A matrix? A matrix is given as 3, minus 1, minus 1, 3. They are similar matrices. The first point is determinant. Determinant, what is the determinant here? 4 2s are 8. What is the determinant here for A matrix? 3 3s are 9, minus 1 which is nothing but 8. So determinant is equal for both the matrices. A for A matrix and B matrix, determinant is equal. What is the rank? Rank. Determinant is not equal to 0. So rank of the matrix is 2. Here also rank of the matrix is 2. What is the trace of the matrix? Trace of the matrix. Here trace of the matrix. Eigenvalues also will be equal. So that's why A and B are similar matrices if this condition is satisfied. This condition is very important. Similar transformation from one basis to another basis. So very important problem. This is for 3 by 3 matrix. Already we have done for 2 by 2 matrices. Okay. Reduce the matrix A equal. this one to diagonal form. Diagonal form in the sense we have only diagonal elements alone exist. So that's called a diagonal form. Diagonal elements will be there. So those matrices are called diagonal form. So to diagonal form by similarity transformation. So similarity transformation, they will have to obey this formula. Okay, that's called similarity transformation. Hence one can find out A cube. Let us see. Okay, once we can find out A cube. So first we will go with the characteristic equation. The characteristic equation is given by this formula A minus lambda I det. Then we will have to get this characteristic equation. Correct? See, characteristic equation is given as 1 minus lambda multiplied by 2 minus lambda multiplied by 3 minus lambda minus 0. Okay, 0 multiplied by minus also 0. And here just take this and that also 0. This also will be 0. So 0 0. So your characteristic equation is given by this. So immediately one can find out the eigenvalue will be 1, 2, 3. So eigenvalue will be 1, 2, 3. Okay. Now we are going to find out the eigenvectors. So substitute lambda equal to 1 first. So in this equation. So we have this equation 1 minus lambda. You substitute lambda equal to 1 here. So when you are going to substitute 1 here, you will have 1 minus 1. So 0. So 0 minus 1 2 0 1 minus 1 0 0 2. A minus lambda I x1 equal to 0. Correct? So we have x1 x2 x3 0 0 0 here. So now this multiplied by this multiplied by this multiplied will have this equation. Similarly for the second one you will have this equation. Similarly for the third one you will have this equation. Now immediately you can find out 2x3 equal to 0. It implies that x3 equal to 0. So immediately you can say 2 cannot be equal to 0. Only x3 can be equal to 0. So x3 equal to 0. If x3 equal to 0, x2 must be 0. Is it okay? x3 equal to 0. x2 equal to x3 here. See here x2 equal to x3. x3 equal to 0. So x2 must be equal to 0. So now x3 equal to 0. And what about x1? x1 is not there. Correct? x1 is not there in the equation. Already we have x3 equal to 0, x2 equal to 0. We should not put 0 here. So minimum value will be 1. So x1 equal to 1. Is it okay? So your eigenvector will be capital X1 equal to x1, x2, x3, which is nothing but 1 0 0. Is it okay? Now we will go for next eigenvalue, lambda equal to 2. So lambda equal to 2 implies just substitute here in the A minus lambda I that matrices. You will have lambda equal to 2 means 1 minus 2, which is nothing but minus 1. So we have minus 1. Minus 1. Here it is nothing but 2. So here it is 0. 2 minus 2, which is nothing but 0. So next one will be minus 1. Again it is 0 0. So 0 0. 3 minus 2, which is nothing but 1. So multiplied by x1 x2 x3. Here it is 0 0. So first will be minus x1 minus x2 plus 2x3 equal to 0. The second equation you will have x3 equal to 0. So oppose minus x3 equal to 0 implies that x3 equal to 0. So x3 equal to 0. So if x3 equal to 0, you have minus x1 which is equal to plus x2. Correct? See, if x3 equal to 0, we have already done x3 equal to 0. If x3 equal to 0, substitute here, we have minus x1 equal to plus x2. x1 equal to minus x2. Correct? If x1 equal to 1, x2 will be minus 1. If x2 equal to 1, x1 will be minus 1. We can write either way. I repeat, see here, you have minus x1 equal to plus x2. If x1 equal to 1, x2 will be minus 1. So x2 will be minus 1 if x1 equal to 1. Is it okay? So you have capital X2 equal to eigenvectors are 1, minus 1, 0. Similarly, we will have to use lambda equal to 3, the last eigenvalue. So lambda equal to 3, you substitute in this matrix, you will have this matrix multiplied by the eigenvectors, we will get these equations. So minus 2x1 minus x2 2x3 equal to 0. the second equation becomes minus x2 minus x3 equal to 0. Okay, it implies that minus x2 equal to plus x3. Already we have substituted 1. So you have to go only with the next one, which is nothing but x3 equal to 2. If x3 equal to 2, x2 will be minus 2. See, 2 minus 2. Then substitute here. x3 equal to 2, you substitute here. So this becomes 4. Then x2 equal to minus 2, you substitute, that will become plus 2. So minus 2x1. Minus 2x1, 2 plus 4 are 6. Here you have minus 6. Minus minus will get cancel. 2x1 equal to 3. So your x1 becomes, here it is wrong, 2x1 equal to minus 6. So this one will get cancelled. You have x1 equal to 3. Correct? So here it is wrong. Here x1 equal to 3. Is it okay? Minus 2x1 equal to minus 6. Minus minus will get cancelled. 2x1 equal to 6. So your x1 will be 3. So x1 is 3. This is wrong. x1 equal to 3. So you have the last eigenvectors will be 3 minus 2, 2. So we have found out 3 eigenvectors. See, we have found out 3 eigenvectors. The first column eigenvector, second eigenvector, and third eigenvector. Okay. Now put together, we are going to make all these 3 eigenvectors put together in a matrix, what we call this as model matrix. You have to go with eigenvectors. This is first eigenvector. This is second eigenvector. This is third eigenvector, which is nothing but your model matrix. Is it okay? Model matrix. Now let us take determinant of this model matrix. Determinant of model matrix will be minus 1 multiplied by 2. So that will be minus 2. Other things are all 0. So determinant will be minus 2. How to find out the adjoint m? Cofactor transpose of the cofactor. How to find the cofactor of m? Cofactor. So you have to take first this one. You have to take this minus first. So you have to take. Similarly, you have to go with this one with a minus sign. So you have to take this one with a plus sign. Similarly, we have to take this one, this determinant with a minus sign. Then this will have plus sign, this will have minus sign. So you have to include minus plus, that sign also very important. Then after that you have to take the transpose. So you will have adjoint. Adjoint is given as this. Is it okay? We have taken the cofactor, transpose. We will have to take the cofactor, then transpose. That will give you adjoint. So your adjoint is here. So m inverse will be adjoint divided by mod m. So adjoint is here, divided by mod m is minus 2. So minus 2 divided by 2, that minus 2, that will give you 1. Then minus 2 divided by minus 2 will give you 1. Minus 1, no, plus 1 divided by minus 2 will give you minus 1 by 2. Is it okay? So your m inverse is this. So we have found out m inverse. What is the formula? P inverse AP. But here it is m inverse AM. Both are equal. Okay. So in those 2 by 2 problem, we could find out only P inverse AP. But here it is m inverse m. So m inverse is here, A is here, m is here. So on solving all those things, matrix multiplication, you will get exactly diagonal matrices. See 1, 2, 3. What is the problem? What is just look at the problem. 2 diagonal form. So you are going to reduce this matrix to diagonal form through similarity transformation. So we have reduced into diagonal form. See 1, 2, 3. So those 1, 2, 3 are surely eigenvalues. 1, 2, 3. Can you remember? 1, 2, 3 are eigenvalues. See here. 1, 2, 3 are eigenvalues. So after the similarity transformation, again we will be obtaining only the diagonal matrix, which is nothing but your eigenvalues. 1, 2, 3. So your diagonal matrix will be m inverse. We have done m inverse AM. Now eigenvalues of A and D. So this is your D. Diagonally, we have diagonalized. So this is not diagonal, so we have diagonalized. So D matrix, this matrix and A matrix, they will have same eigenvalues. You just look at here. See, this is your A matrix. Eigenvalues are 1, 2, 3. This is your D matrix. Eigenvalues are again 1, 2, 3. So both will have same eigenvalues. So they are called similar matrices. And now the question is to find out A cube. Your question is to find out A cube. So D is given as this. As we discussed earlier, you will have to pre and post multiplied by m and m inverse. M and there we multiplied with P inverse and P. So you are going to multiply with m and m inverse, P and post multiply. So you will get A equals m d m inverse. Okay. Now we need to have only A squared. So A squared is this multiplied by this. M inverse m. What is the answer? M inverse m. M inverse m. P inverse P. What is the answer? I. So you will have I here. And this m is here. Your d squared. D multiplied by d will be d squared. So your m inverse. Again that will be again m inverse. So you have m d squared m inverse. So similarly you can have this is for A squared, and similarly you can have A cube. Again you will get only D cube. So m d cube m inverse. A to the power 4, that also will be m d power 4 m inverse. A to the power 100, m d to the power 100 m inverse. So you can have any higher powers. So your m is here model matrix, and D is the diagonal matrix which we have obtained, correct, diagonal matrix, and m inverse is here. On matrix multiplication you will have A cube. So we have found out now A cube. Any doubt? Any doubt here?